Okay, next we're going to talk about water molecules and how they can both attract to one another and attract to other substances. Water molecules exhibit both cohesion and adhesion. What's cohesion? It's the tendency of water molecules to stick together. It's what produces surface tension. It's the reason that the basilisk lizard can run across the surface of water, or a water strider can skate across water. It's essentially the tendency for a water surface to resist being broken. It explains why a belly flop hurts. Here we can see both cohesion and adhesion in the image on the left. The cohesion is the water molecules sticking to each other to create larger water molecules, or droplets. The adhesion is the water molecules sticking to the spider's web. Over on the right, we can see surface tension being illustrated. We can see that there's a slight bend to the water where the legs of the water strider touch that body of water, but they're using the overall hydrogen bonding between water molecules, thanks to its cohesive properties, to skate along the top. So we've talked about cohesion, but we also want to talk about adhesion because water exhibits both. Adhesion is the tendency of water molecules to cling to other substances. It actually results in something that you've probably seen utilized, capillary action. That's when there is the movement of water into very narrow spaces, like the tiny cavities in a water-filled paper towel. Land plants also use cohesion, adhesion, and capillary action. They want to supply water to all parts of the plant. So as water evaporates from the leaves, it creates an evaporative pooling called transpiration pool. And with water adhering to the walls of the vessels and adhering to itself, we're able to see that capillary action allows water to move against gravity. And the result is that water can travel from the soil and then throughout the plant to the stem and the branches and the leaves. And water also interacts with many other molecules. It's a great solvent. What is a solvent? It's a substance that does the dissolving. It's usually present in greatest amount compared to something that dissolves, often called a solute. Water may be an excellent solvent, but it's not truly universal. It can't dissolve things like lipids, so fats and oils. The reason, though, it is a good solvent for things that are charged, things that are similar to itself, that are hydrophilic or water-loving, is because it's able to surround and disperse the atoms or molecules of another substance. And when that occurs, the solvent, water, dissolves the substance. Again, another name for that substance is a solute, and when a solvent with one or more solutes, dissolved substances, exists, that's called a solution. So water may be a great solvent, but it is not truly universal. It's not the universal solvent. It can dissolve, though, well, ions and molecules that are hydrophilic, that are water-loving, and can be coated by the components of water. But larger, nonpolar molecules will not dissolve in water. A lot of those molecules are hydrophobic or water-fearing, and they tend to sequester themselves away or in droplets that don't mix with water, like fats and oils. Water also moderates the effects of temperature changes, and it takes a lot of energy to heat water. That's because water has a high specific heat. So when you go to the beach in May and it may be just hot enough, the water's still probably freezing because it takes a lot of heat to heat up a body of water, even 1 degree Celsius. So that high specific heat is due to hydrogen bonding of its molecules. So that hydrogen bonding has a lot to do with the characteristics and properties of water, both when we're talking about cohesion and adhesion, things like surface tension and capillary action, but also when we talk about its high specific heat, or the ability of water basically to resist heating up for quite a while. Water also has a high heat of vaporization, which is what makes sweating such an efficient cooling system. What is meant by a high heat of vaporization is that it takes a lot of heat to cause water to go from a liquid state to a gaseous state. And when it does evaporate, when it goes from liquid to a gas, it takes that heat with it. So on our body, we have sweat glands. And sweat glands produce sweat, which is mostly water. On the surface of our skin, that sweat absorbs heat, and when it does finally evaporate, it takes that heat with it, cooling the skin. So that's an example of high heat of vaporization, which means there is a high amount of heat needed to cause a substance to evaporate. Water is also unusual in that when it goes from liquid to solid versus liquid to gas, when it forms ice, it's actually forming something that is less dense than liquid water. Usually when something becomes solid, it's denser, but that's not the case with water. Water forming a solid actually makes it less dense, and that means that we can have bodies of ice on top of bodies of water. That's why icebergs and ice cubes float, because they're less dense, less heavy than liquid water. And that's because when something freezes, with the structure that water has, it actually causes the molecules to expand out in a more organized lattice structure, and the molecules end up not being as close together. So you can see how liquid water on the left is more dense, therefore more heavy than the ice or solid water on the right, which is more lattice and structured and organized. And that's a great characteristic for water because it protects aquatic life. It allows aquatic life to persist below the surface. It prevents freezing of these deep depths of bodies of water. So ice floating on ponds and lakes forms actually an insulating layer and is protective as opposed to dangerous to aquatic life. Something else we can look at is pH. And we usually start with water-based solutions and how they can be changed to something that's acidic or basic or something that stays neutral. Because at any given moment, a small fraction of water molecules could break apart and become a hydroxide ion, which is OH negative, or a hydrogen ion, which is H positive. When you're looking at a beaker of neutral water, you have an equal amount of positive and negative charges, even if some of the water molecules have separated into hydroxide and hydrogen ions. But if you start to see an increase in hydroxide or hydrogen ions, you may start to see your substance become more acidic or basic, but it would move away from an equal concentration or neutral solution. Because pure water contains equal concentrations of OH negative or hydroxide ions and H positive or hydrogen ions. So when a substance releases hydroxide or hydrogen ions, we're going to disrupt that neutral solution. And when we add hydrogen ions, when they exceed the amount of hydroxide ions, we say that solution is now acidic. So acidic substances or solutions, they tend to have more hydrogen ions than hydroxide ions. They also tend to release hydrogen ions over hydroxide ions when dissolved in water. A great example is hydrochloric acid. When you put hydrochloric acid in water, it releases more hydrogen ions, or H+, instead of hydroxide ions, which is OH negative. Examples of acidic solutions include many citrus fruits like lemons, also vinegar, also known as acetic acid. So those are examples of acidic solutions that have more hydrogen ions than hydroxide ions in their solution. Now, if you do the opposite, if you're looking at a solution that has more hydroxide ions than hydrogen ions, you're looking at something that's alkaline or basic. A base increases the amount of hydroxide ions, especially its concentration when dissolved in water. So a counterpart to hydrochloric acid is sodium hydroxide. Sodium hydroxide is a base that separates into sodium and hydroxide in water, that hydroxide being the hydroxide ions that make it very basic or alkaline. A lot of cleaning solutions, soaps, antacids, those are examples of bases. And we measure how acidic or basic a solution is by measuring the amount of hydrogen ions using the pH scale. That's what the H in pH scale is for. It's a measurement of the amount of H's, the amount of hydrogen ions. So if something has more hydrogen ions than hydroxide ions, it's acidic, and it will have a pH somewhere around 0 to 6. If it has more hydroxide ions than hydrogen ions, then it's going to have a pH around 8 to 14, and it's considered basic or alkaline. And a pH of 7 is considered neutral, where you have an equal number of hydrogen and hydroxide ions. You can actually use readily available litmus paper. Some people use this, for example, in pools, and it's going to stain a certain color to let you know if something is acidic or alkaline, so acidic or basic. Blue litmus paper tends to turn red under acidic conditions, and red litmus paper turns blue under alkaline conditions. There's other types of litmus paper that have different ranges of color changes, represented usually on a graph on the bottle. So here's our basic pH scale. Again, the pH scale measures the amount of hydrogen ions. If you have more hydrogen ions, something is more acidic than something with less hydrogen ions. Examples of acidic substances are citrus fruits, colas, tomatoes, coffee, stomach acid. whereas we get closer to a neutral pH with things like milk and blood, but something that is truly neutral and has an equal amount of hydrogen and hydroxide ions is pure water. And then we move to the alkaline or basic side of the pH scale when we talk about baking soda, antacids, things like bleach or ammonia. A lot of cleaning products are going to be basic or alkaline. You can also see from this image that the pH scale goes from 0 to 14, with lower numbers being more acidic than the higher numbers, and 7 the neutral pH being in the middle. The scale is also logarithmic. What is meant by that is if you compare something that has a pH of 1 to something that has a pH of 2, the substance with a pH of 1 is 10 times more acidic than the substance with a pH of 2. Or if we compared a substance with a pH of 10 to a substance with a pH of 12, then the substance with a pH of 12 is 20 times more basic than the substance with a pH of 10. So every increase or decrease is on the order of 10. That's what is meant by it being logarithmic. Here are some basic characteristics for acids and bases. While acids usually have a sour taste, bases are usually bitter. You can eat some acids like citrus fruits, but all acids produce hydrogen ions in solution when dissolved in water, whereas hydroxide ions are produced in solution when you dissolve bases in water. We looked at the litmus test and we see that for acids, it turns blue litmus paper red, and bases turn red litmus paper blue. One of the biggest giveaways that something might be a base is it's slippery to the touch, like a lot of cleaning products. Bases can be used to neutralize acids, just like acids can be used to neutralize bases. And examples like lemon, vinegar, which is acetic acid, and coffee are common acids that you've probably come into contact with. And examples of bases are soap and borax and ammonia and sodium bicarbonate. So some of these are daily cleaning products, some of them are very dangerous, some of them you can actually consume, but they're all general descriptions of acids and bases. And one of the last things we're going to talk about is a buffer. A buffer is a molecule that helps maintain a solution at a nearly constant pH. It essentially helps resist large swings in pH, and it does that by accepting or releasing hydrogen ions in response to small changes in hydrogen ion concentration. For example, if you start to see an excess or increase of hydrogen ions, a buffer system will combine those hydrogen ions and tie them up in another molecule to make them less interactive with the surrounding solution and make the solution less acidic. If you start to see an increase in hydroxide ions or a decrease in hydrogen ions, then a buffer will release hydrogen ions from those molecules where they had previously tied up those hydrogen ions in order to add hydrogen ions and make a solution less alkaline and more acidic, essentially maintaining a pH or keeping it near neutral. Humans actually have a buffer system built into their blood. It's called the bicarbonate buffer system. So this buffer system responds to a rise in pH by breaking down carbonic acid into hydrogen ions and bicarbonate ions. That excess hydrogen ion will decrease the pH because excess hydrogen ions make things more acidic and will bring the solution back to kind of a normal or stable pH. Whereas if there was a drop in pH, the hydrogen ions and bicarbonate ions created by breaking apart carbonic acid would recombine, and that would tie up free hydrogen ions that contribute to pH changes, and that would actually make the solution a little bit more alkaline or keep it from becoming too acidic. So resisting large swings in pH, that is the main role of a buffer system, and humans use their built-in buffer system in order to carry out this process. But there's also chemical buffer systems and a protein buffer system and others that exist inside living things. And as far as chemistry and looking at the material of Chapter 2, that's it. Make sure to catch all the videos.